Thank you very much once more, Robin. I definitely will not fulfill your expectation, but hopefully I will try my best in this short time. And I will talk about some news, but we'll be careful with talking about the novel imaging systems, but give you at least an insight. So I will start with a little bit background, and perhaps you make notes if you do not understand this context. So there are, for our opinion, only two really accepted views of tinnitus along all the numerous controversial theories which exist. So there is a consensus that tinnitus is linked to elevated subcortical spontaneous activity. And this is generally accepted. Hyperexcitability somewhere in the way. Although the source of this hyperexcitability is not very well described and identified. And then the second is that the elevated spontaneous activity is assumed to lead to tinnitus perception through driving a decline of alpha brain oscillations linked to enhanced gamma brain oscillations at rest. Emphasis on rest. And this has been shown in temporal lobe from a lot of people which you know, or Sudirida, Van Nest, Weiss, Obleza, Linas, Güntenberger, and others. And here again, although the source of the reduced thalamocortical processing, this is reduction of alpha oscillations in the brain, is also not identified. So it's not specified. So it's currently assumed, and also there it's a hypothesis, that a typically alpha-like oscillation power in the brain, which we, whenever we hear sound, is decreasing. So alpha oscillations decrease when we hear sound. And because in tinnitus, the alpha oscillations are already low, our brain is expected to hear it as a sound. So in tinnitus subjects, it's hypothesis to be sensed as an internal sound. This is, for example, the view of Weiss, Obleza, probably Derrida, and all the people agree, and this is what we call prediction error, or whatever it is. A lot of discussion about this. So we have addressed two main questions. The one is, what is the source of the elevated subcortical spontaneous activity? So this hyperexcitability in tinnitus that leads to cortical brain changes and is predicted to lead to tinnitus. And can we reproduce previous finding of altered alpha brain oscillations at rest in tinnitus subjects with the OPM technique? Which I will explain soon, and hoping that we can improve the insight in brain activity changes in tinnitus. And I will start with this little screen here. So with the first hypothesis, which we think is generally accepted. So there is a hyperexcitability as an accepted neural correlate of tinnitus. But, now the but comes, there are two views, two totally contradicting, a little bit contradicting views, how this hyperexcitability exists. And oversimplified, I sketched this like this. So this is the one view. It's assumed that it's linked to a loss of a distinct fiber, the low auditory fibers with a high activation thresholds, and they lead to an increase in excitability following a loss of phasic inhibition, transient inhibition, and this leads to central neural gain, and this could be a source of hyperexcitability in the brain. And then there is another view. We are the few which share this, that we think that it's a loss of these low firing rate fibers with a so these high spontaneous firing rate fibers with a low activation threshold. And this would lead to hyperexcitability due to a loss of tonic inhibition. Here, phasic inhibition, here, tonic. If someone has a question to this, I can explain later on. And this leads just to the opposite, to a loss of central gain, and thereby through a loss of synchronicity and tinnitus. So there are meanwhile also from other fields some studies who also agree that this is not tinnitus, and it's not only Polle, but also Sedley said it some, and Salvi and others, while we and Fang Seng assume that this is more tinnitus. Why we think this? Because another accepted correlate is what I just mentioned, spontaneous. So this is the spontaneous. So these are the brain oscillations, and these spontaneous alpha oscillations are reduced at rest, and gamma oscillations are enhanced at rest, as numerous studies, the one shows only alpha, the other gamma oscillations like Van Est or something like this. But this seems to be an accepted correlate as well, and all the neurofeedback and feed-forward training programs are based on this a lot, who want to therapy tinnitus. So, but we think that this is best explained with our model, because this reduced thalamocortical input could be best covered, this reduced alpha oscillations, and could explain this. So this weakened transfer of these low threshold auditory fibers, we can call them also silent fibers, because they are responsible for determining silence in our perception. So the weakened transfer of these low threshold fibers explain both accepted tinnitus correlates. What are the predicted consequences for cortical brain oscillations if we could measure them? So if this is this model, so this is this model of the low firing rate fiber loss and neural gain, then we would predict that the baseline would keep totally normal, because these fibers do not contribute to the baseline and to synchronicity, and we would have preserved alpha at rest, and we would have likely enhanced task-evoked brain oscillations. While when this model is correct, then we would see that there would be a loss of the baseline, because loss of sustained inhibition, and this was changed the operation point in the cortex, and this would lead to reduced alpha at rest and to reduce task-evoked brain oscillations. So let's see what comes out. So our clinical study is designed so that we include controls and tinnitus subjects, and we currently, we do all, but in this study which I present here, we excluded tinnitus hyperacusis, which we perfectly can distinguish and identify through scores and uncomfortable loudness level. I will not go in. But what we see here for you important, that when we do this, we include tinnitus without a comorbidity of hyperacusis, then we see no differences in the hearing threshold. So this means confirms what we think, that tinnitus is not causally, emphasis on causally related to a hearing threshold loss up to 16 kilohertz here. And when we look then for supra-threshold auditory waves, so this is the analysis of the peak amplitude, we confirmed what we saw 30 years ago already in animals, 15 years ago in animals, repeatedly now in humans, that in tinnitus we see a reduced, so these are the wave of the peaks. This is the auditory nerve, this is mid, and this is the inferior colliculus response. It's reduced, and the response is also delayed. So we see our phenotype, which we typically see in tinnitus subjects, where aged and hearing matched subjects exhibit fast auditory processing deficits. So what can we do with optical pump magnometer? And I will briefly explain what this is at all for those who are not familiar with this. So typically this is an MEG, a typically classical squid MEG, which most of you will know. And here are sensors, and they measure the neural activity through magnetic fields. But here the sensors are a little bit far away from the cortex. This is a disadvantage. There is another disadvantage, that there are high running and infrastructure costs. So there is a greater distance between sensors and the scalp than in OPM sensors. So this is the OPM, an optical pumped magnetometer. The principle is a little bit different, but it's very sensitive. The sensors are sitting here on the scalp, and it's said to have a higher spatial resolution. And it's said, and this is the big advantage, it has no running cost and no infrastructure costs. And this is a little bit revolutionary, it would be possible to do it in the clinic itself, what is not possible currently with a squid MEG. So in our clinic, we were lucky to get it through a third money supply. It's in the 3rd floor of the ENT clinic. We put the whole thing in the proof chamber so that we can really measure the acoustic stimuli and whatever we want. And when you look in, you see that in this chamber we have a magnetic shield. The subjects are currently still laying, but to the end they could also sit, and we have a helmet, meanwhile, from 64 sensors, and we optimized it for 1 or 2 years now. And what we can see is this is a previously finding of a squid MEG, so of a classical squid MEG. This is the auditory evoked field potential, a typically butterfly plot, and you measure then this peak here, and this is typically from 20 subjects. And you see here dipole, and this is in the response of a tone. You see it here in the temporal superior lobe. And what you can see here with our OPM is quite surprising and very motivating. So we see here the same butterfly blot, but instead of 20 subjects, we see it with 1 subject here. This is 1 subject. And we see the same depolarization, dipole polarity, but we see 3 times, so this is femtotesla, 3 times higher sizes with 1 patient instead of subjects instead of 20. And this can be performed, for example, when we give a tone paradigm. Here, this is a Satora paper in Nature in 2016. When we present a tone, then we see a typically right hemisphere dominance on the superior temporal lobe. And this can be seen here on these subjects with 22 subjects, and we see it here in the same form with 1 subject. And when we now look to the tinnitus subjects, we see that indeed alpha at rest, you can recall that we saw that there is a previous finding, a general accepted view, that there is a reduced alpha at rest in tinnitus subjects. These are the tinnitus subjects. And you see here, this is lower. So the brighter it is, the more yellow, more activity, and you may appreciate that this is lower than here. And when we look to gamma oscillations at rest, we see that this is here higher than here. I hope you can see this. So this means that we indeed can confirm previous findings of a lot of subjects, and thereby we could have a good precondition which links all the following findings from us to previous findings. So tinnitus at rest is reduced in alpha and linked to elevated gamma as shown before. So first, and I will show you only 1 or 2 slides anymore. So the elevated gamma at rest here, so this is more yellow than here. This is the tinnitus situation. This is the control situation. So the elevated gamma here is linked to a reduced evoked gamma. So here it's elevated at rest, and here it's reduced in comparison to here. Here it's lower, this is higher, this is lower, this is higher here, and this is lower. And you may also appreciate that also on the left side, this is more darker, means less activity. And these are both superior temporal lobe. We can speak about the other findings later on, but this means that this is the previous model, this is our new model, and this here, this reduction, so this elevation at rest, shows us that there is an elevated baseline level. in the cortex, elevated noise level in the cortex, and this elevated noise level is linked to a reduced evoked gamma response. So just as we would predict, so reduced alpha, evoked alpha at rest, linked to elevated gamma at rest, and a reduced tinnitus response. So we can conclude that the elevated spontaneous and reduced tone evoked gamma activity in the auditory cortex overturn previous neural gain theories of tinnitus percept. And with this, I can conclude that we currently assume that the elevated spontaneous activity linked to loss of lateral phasic inhibition is no tinnitus. The deafferentation of this does not explain slow and fast oscillations predicted to be linked to tinnitus. So this fiber model does not explain tinnitus, but this model with a reduced thalamocortical input perfectly explain previous findings. So the elevated spontaneous activity linked to a loss of sustained tonic inhibition following the loss of this may explain alpha at rest and elevated gamma at rest, as in previous studies, and explains tinnitus through less effective cortical inhibition due to a lost contribution of tonic inhibition post-weakened fiber, high firing rate fibers. So this leads to a lowering of the operation points in the cortex. And this explains everything what currently is due, because this is transient. It explains fluctuating tinnitus. It explains more stress, because the whole intracortical pathway would be changed, because the operation point for cortical inhibition would be changed. So with this, I thank, and I will leave this here that we can have a basic for later on discussion, or we can hear the next talk. Thank you so much.